Okay, guys. So here's the next two problems on the free response question. All right. Okay. Right now, we're going to work on problem number C, or letter C. It says the boiling point of bromine 2 is 332 Kelvin, whereas the boiling point of bromine chloride is 278 Kelvin. Explain the difference in boiling point in terms of all the intermolecular forces present between the molecules of each substance. So we talked about this a little bit last week. I'm going to go ahead and just review that with you guys real quick. I'm going to go to my exam resources. I'm going to go to unit 3.1, and we're going to talk about intermolecular forces. Okay. So I'm going to just kind of go through it real quick one more time. We already know, I think we have a pretty good idea of what intermolecular forces are. These are the forces that exist between molecules. And there's different types, okay? So the first one that we're gonna discuss is called a dipole-dipole, okay? This occurs between two polar molecules, okay? You'll know it's a polar molecule if it has a distinctly negative or distinctly positive edge. So when we're talking about ionic compounds, I'm sorry about my handwriting, but I have a new little pad because I forgot mine at home. And it's a little bit different. So we're talking about all ionic compounds, okay? Ionic compounds basically bond based on charge, right? You have one distinctly positive side, one distinctly negative side. And that differences in electronegativity is what creates polarity, okay? So when you're talking about a dipole-dipole interactions, you're talking about two polar molecules that are attracting to each other based on their opposite charges. So here we have water, as you can see, right? Here we have water. We have the distinctly positive edge or side of the water molecule. Let me go ahead and switch that. You have the distinctly positive side of the water molecule being attracted to the distinctly negative side. I'm going to write that with a slightly different color so we can see it better, but attracted to that negative side. And then what we have here is that attraction in terms of water is a hydrogen bond, okay? But it is a dipole-dipole interaction, okay? Dipolar, that's what it means, okay? Examples of polar molecules include things like carbon monoxide, nitrogen trifluoride, et cetera, methane and chlorine, okay? Let's see. Now, the strength of these interactions are going to depend on the magnitude of the dipole. The greater the dipole moment, the greater the interaction. So what this means is more polar, okay, is going to equal a stronger attraction, right? And remember that polarity comes in terms of the differences in electronegativity. Remember, electronegativity is that desire to gain electrons, okay? A dipole-induced dipole. Okay, so when does this happen? Well, here we have water again, right? Here we have the distinctly negative side. Here we have the distinctly positive side of the molecule, right? So water we can see is polar, right? It's polar. This is the positive side. This is the negative side. Now, when we have a dipole-induced dipole, what that is it's an interaction between non-polar molecules, okay? All right, let's see here. All right, so it's between a polar and non-polar molecule, okay? I just wanted to make sure that I was not giving you guys wrong information. So here's what happens, guys. When you have the interaction between a polar molecule and a non-polar, okay, is that negative charge, right? The negative charge repels the electrons away, right, from itself. And what it does is it pushes all those little electrons. Let me switch colors here. Let me get this one. Over the white, okay? What it does, it gets all those little electrons and it kind of pushes them away, right? Because remember, similar charges repel each other, right? So what it does is it pushes all the electrons towards one molecule, right? Or one of in the compound. And what that does is for a split second, it creates a dipole in a non-polar molecule, right? So you have all the positive charges of it on one side, and you have all the negative charges for a split second. And when that happens, then you create an attraction right here. Okay? This type of interaction, when this happens, is called a dipole-induced dipole, okay? And that's what it means. What it means is that it's creating a dipole, or it's creating a slight polarity in a molecule that's typically not polar, okay? When that happens, you're basically creating another dipole-dipole moment, except you're doing it in a molecule that's not typically polar, all right? So that's kind of what's happening in a dipole-dipole-induced interaction, okay? Now, the last one that we're going to talk about is London dispersion forces. This is something that we kind of started talking about before, but we didn't really get to finish it. Basically, all molecules exhibit LDFs. Even polar molecules exhibit LDFs, okay? And basically, this is just the type of interaction between non-polar molecules, all right? So if you're working with molecules that are non-polar, and how do you know whether something is polar or not, okay? Well, I showed you guys, let me show you guys. If I have the, see, reference, go to reference. Here is our electronegativity chart, okay? So here it is, okay? Now, what this is telling you, okay, it tells you the amount of electronegativity that exists in these elements, okay? Now you can see that the more you go to the right, where's my little chart here? The more you go to the right, the greater the electronegativity. So electronegativity increases in this direction on the periodic table. Negativity. Again, I'm sorry for the handwriting. It's just a different pad. It's not working as good as my other one. Okay, so electronegativity increases to the right of the periodic table, and it increases as you go up the periodic table, right? So as you move up the table, you're going to see an increase in electronegativity. And because of that, the most electronegative element on the periodic table is in fact fluorine. Okay. Now, how do you measure polarity? Well, let's do a quick example. Okay. Let's say I have sulfur, S2, right? Is S2 a polar molecule? Well, we can take a look at the value of the electronegativity. So there's 2.5 for sulfur, and we're going to subtract 2.5 from sulfur, and we're going to see that that's 0. There is no difference in electronegativity, right? If there's not a huge difference in electronegativity, then we call this nonpolar. Nonpolar. Let's take that same compound, that's the same molecule, right? And let's do it with sodium. NaS. Well, the sodium has an electronegativity of 0.9. Sulfur has electronegativity of 2.5. So if I take the difference from 0.9 and 2.5, I end up with a difference of negative 1.6. This is a pretty large difference. So right here, we would say that this is polar, right? So when I say that polarity depends on the amount of the difference in the electronegativities of the things that are bonded, that's what I'm talking about, right? Their electronegativity values. Now, obviously, you're not going to memorize this table, but just understand that if molecules are bonded to each other on this side of the table, right? For example, let's say you have chlorine bonded to itself. You got to recognize that that's already going to be a nonpolar because you're going to be subtracting the same electronegativity from itself. So you should just know that this is going to be a nonpolar molecule. Now, if it's nonpolar, then the interaction forces are going to be LDF, London dispersion forces, right? If they're polar like this, then you're going to say that's a dipole-dipole, right? Dipole-dipole, right? And then when you have one that is polar and one that is nonpolar, we call that a dipole-induced dipole interaction, okay? That's what I'm talking about. Now, if you bond two elements from the right, okay, for example, let's say you have chlorine somehow bonded to bromine, right? Okay, in a covalent bond. Well, the differences here is going to be 2.8 minus 3.0, it's not going to be a whole lot of difference. It's going to be a 0.02 difference. So what you have here is you do have a slight polarity, but the London dispersion forces are going to be the most prominent forces because the polarity is very, very minuscule. It's very, very small. So understanding what the electronegativity is, or the differences, is going to help you understand what makes things polar and what makes things non-polar. Remember, electronegativity is just the desire to gain electrons. You know, as you go across the period on the periodic table, you're getting closer and closer to filling up that last valence shell with these electrons, right? And the closer you are to filling up the electron shell, the more desire you're going to have to pick up more electrons. So if you have a greater desire to pick up more electrons, you're going to be much more electronegative. And if you're bonded to something that is much less electronegative, you form a polar compound, okay? That's why water is a polar compound, because you have a value of 2.1 at water here, see at hydrogen, and oxygen has a polarity of, electronegativity of 3.5. So the difference between those two electronegativities leads to create a polar molecule, okay? All right, so let's go ahead and go back to our work here. Okay, so here we have these two compounds. Yes, let me see here. Sorry. All right, so these are the types of molecules, or I'm sorry, forces that we're going to see, okay? Now, when we have London dispersion forces, okay, what this does is the same thing as a dipole induced. It kind of induces a dipole moment for a split second. And what it does is you see the interactions here where the shift in electronegativity, or this shift in electrons, creates areas of the molecule that are slightly more negative and some that are slightly more positive. When that happens, they kind of attract the ones that are slightly more negative and the ones that are slightly more positive. And you have this interaction that happens here, okay? This interaction is kind of like a hydrogen bond, but it is an interaction based on charge, and that's called the London dispersion force, okay? Now, the strength of the LDF is going to depend on how easily the electrons can disperse, meaning how easy can these electrons, for example, here, shift in this direction, right? And that's going to depend on the size of the cloud. So a bigger electron cloud, okay, a bigger electron cloud is going to allow for a bigger dispersion, okay, of electrons, right? So if you have much more space for these electrons to kind of move around, okay, then you're going to have a much stronger LDF, okay? Basically, as you move down the periodic table and the elements become bigger and bigger, then you're going to form much greater and stronger London dispersion forces, okay? That's how they work. So let's go back to our question then. Okay, so let me delete this real quick. All right, here's what we have. Okay, so it says we have a boiling point of Br2 is 332 Kelvin, where bromine monochloride is 278 Kelvin. Explain the difference in the boiling point in terms of all intermolecular forces between the molecules of each substance. Okay, so bromine, okay, bromine is going to be on one side of the periodic table. So let's go ahead and take a look at our periodic table real quick. So bromine is here. Let me get my pencil here. Is this guy right here. Okay, so the first compound we have is bromine bonded to itself, and the other one is bromine bonded to chlorine, which is this guy right here. Okay, so here we have the two compounds. Let's go back to our space. Okay, so the first one that we're going to deal with is the bromine. So I can already see that this is bromine bonded to itself. So it's going to have a very, it's going to be a nonpolar. Now, how do I know that's going to be nonpolar? Well, when something is bonded to itself, right, then you have no difference in electronegativity. Because if the electronegativity value of bromine is 3, and we'll verify that, oh, it's 2.8, right? If the electronegativity value of bromine is 2.8, sorry, and it's bonded to itself, then that's going to give me 0 difference in electronegativity. Now, you don't have to do this calculation. I'm just showing you guys so you guys can understand what it is. But I already know that bromine bonded to itself is going to be nonpolar. So the primary interaction that's going to happen here is going to be an LDF. It's going to be London dispersion forces because this is 2 nonpolar. This is a nonpolar molecule. The other one that we have is bromine monochloride, okay? Now, this is also nonpolar, but it's slightly polar because if you look at bromine, bromine is 2.8, okay, and chlorine is 3.0. So if you have both of these, you have a slight polarity at 0.2, right? You have a slight polarity at 0.2. So this one is going to have a dipole-dipole, very, very small, right? And it's going to have an LDF. Those are the types of intramolecular forces that we have in this one. Now, because this is a much bigger molecule, right? Because bromine is definitely bigger than chlorine because it's in, it has another electron cloud because it's in a higher energy level. So bromine, right, is higher energy level. And it has another extron cloud, a bigger cloud. Then the London dispersion forces are going to be much greater than they are in this compound. And because the dipole-dipole interaction is very, very slight, that's not going to be enough to outweigh the LDF that's produced in Br2. So in this compound, because the London dispersion forces are much stronger in bromine, in bromide, right? Or sorry, Br2, then what's going to happen is you're going to have a harder time breaking those interactions, okay? Because you're having a harder time breaking those interactions, it's going to take a lot more energy to break the LDF, which is why bromine, you can see, has a much higher boiling point, okay? And the reason that it has a higher boiling point is specifically for that. The LDF is going to be harder to break those interactions than it's going to be for bromine monochloride, all right? So the stronger the force, the more energy it takes to kind of break those forces away. And this goes back to when I explained to you guys what happens in boiling water, okay? That's why it has a higher boiling point because the London dispersion forces are going to be much greater, okay? All right, next one we're going to do is question D. We're going to do question D. Let's take a look at what it says. This thing never changes color for me on the first time. Okay, question D. It says, calculate the pressure in the container before equilibrium is established. Now, it tells you right here that you have a 1 mole sample of pure bromine monochloride and it's placed in a previously evacuated rigid 2-liter container at 298 Kelvin. Eventually, the system reaches equilibrium according to the equation above. Calculate the pressure in the container before equilibrium is established. Okay, so pressure, okay, anything that has to do with gas, and we know we're working with gas because it tells you right here, gas, okay, you're going to start using the gas laws, okay? Now, there's several to choose from, okay? The first law that we're going to discuss is Gay-Lussac's law, okay? Gay-Lussac, okay? Gay-Lussac has a law that says that the pressure and the temperature of a system, the initial pressure and the initial temperature of the system will equal the final pressure and the final temperature, okay? This has to do with pressure and temperature. Here we see that pressure and temperature have a direct proportional relationship. As pressure goes up, temperature goes up. As temperature goes up, pressure goes up. Remember that pressure is measured as the amount of collisions between gas particles. As you increase temperature, okay, As you increase temperature, what you're doing is you're increasing kinetic energy. Remember, kinetic energy is just the movement of molecules. So if these molecules are moving faster, right, then the likelihood of them crashing into each other is going to be much greater. The more times these molecules crash into each other or into the container, right, the inner wall of the container, then the higher the pressure is going to be. So what we see here is that we have a direct relationship between pressure and temperature. Okay. The next law that we're going to discuss is going to be Charles' law. Okay. Charles' law says that volume and temperature also have a direct relationship. And the initial volume times the initial temperature is going to equal the final volume over the final temperature. And here we see that volume and temperature have also a direct relationship. As volume increases, okay, we see an increase in temperature. Now, if the volume of a container, for example, is not rigid, if volume is able to change according to temperature, remember that as you increase temperature, you're increasing kinetic energy, okay? As you increase kinetic energy, these particles are beginning to move faster. And if your container is not rigid, that's going to increase the amount of volume that's present at any given moment, okay? So Charles' law says that as you increase the amount of temperature or the amount of kinetic energy, if you want to keep your pressure constant, right, then you're going to have to expand the space to allow for more movement. So think of it as like a balloon, right? If you want to keep the pressure at a constant pressure, then you're going to have to make the balloon bigger and bigger in order for it to keep the same pressure. So this Gay-Lussac, right? This is assuming that volume is constant. Volume is not changing. When you're talking about Charles' law, you're assuming that pressure is constant, meaning it's not changing. Okay. The next law that we're going to deal with is Boyle's law. Okay. And Boyle's law says that pressure, the initial pressure times the initial volume is equal to the final pressure times the final volume. Okay. These are units of, this has to deal, assuming that in this case, temperature is constant, okay? So here, temperature is not changing, right? So if you wanna make sure that the temperature is constant, then you're gonna keep it so it's not changing, okay? So temperature is constant, unchanging. What this relationship tells you is that pressure and volume have an inverse relationship. As you increase the pressure in a system, right, you do that by decreasing the volume. If you decrease the volume of an environment or a system, what you're going to do is you're going to increase the pressure, because now the same gas particles have less space to move around in. And because they have less space to move around in, the likelihood of collisions is going to increase. If you have more collisions in a system, you're going to have a higher pressure. So pressure and volume have an inverse relationship. If you decrease pressure, right, you can decrease pressure by increasing volume. So these have an inverse relationship, okay? These have an inverse relationship. Next, we have the combined gas law. And this law just puts everything together. It says that PV, the initial pressure and volume, over the temperature, is equal to the final pressure and volume over the temperature. Okay. If you have a system that has differences in any of these, okay, then you're going to use the combined gas law. Okay. Here, nothing is constant. Okay. Nothing is constant except the number of moles. Okay. Nothing is constant except the number of moles. So I'm going to put here number of moles constant, meaning that it's going to be the same amount of gas, right? It's going to be the same amount of gas. That's going to remain the same, but everything else is going to be variable, okay? The last gas law that we're going to discuss is called the ideal gas law. This is a law that deals with the behavior of gas at ideal circumstances, which is standard pressure and temperature. So the ideal gas law states this, states that the pressure and the volume is equal to the number of moles times the gas constant times temperature. PV equals nRT, okay? P represents pressure. Reset that real quick. So P is pressure. Okay, V is volume. R, or N actually, is number of moles. R is the gas constant, which is going to be on your cheat sheet. Okay, and then the T is temperature. When you're working with gas laws, you always want to make sure your temperature is in Kelvin, which is the temperature in Celsius plus 273. All you got to do is add 273 to any Celsius temperature, and you convert it to Kelvin. Volume is going to be either milliliters or liters. Pressure can be in atmospheres, torr, millimeters mercury, Pascal, kilopascal. These are all units of pressure, okay? And then moles is going to be moles. Gas constant has its own unit, and I'll show you where it is on the cheat sheet in just a minute, okay? Also for reference, remember that 1 atmosphere is equal to 760 torr, if you ever need to convert, which is equal to 760 millimeters of mercury, which is equal to 101.345 kilopascals, which is equal to 101,345 Pascal. Okay, now all these units are also going to be on your cheat sheet, which I'll show you guys in just a second. But this is it. Now, why did I go over all these gas laws with you? Anytime you're dealing with a problem, okay, that deals with gas laws, all you got to do is figure out either what's constant, what's changing, or what's been given. Okay, so let's take a look at our page real quick. Okay, let me see. Pulling up our cheat sheets here. Okay. Let's close this up. Okay, I'm gonna post my cheat sheet right here. And there they are. See, there's your gas law right there. Usually with this law, you can pretty much solve any problem. But in this case, I want you guys to pay special attention. Now, one of the things you're gonna also realize about gases is if you have a container that has several different gases, okay, the sum of each individual gas is equal to the total gas of the container, right? That's what this is. This is the Dalton's law of partial pressures. So let's say you have a container that has 1 atmosphere of gas 1, 5 atmospheres of gas 2, and 6 atmospheres of gas 3, then the total pressure of the system would be 12 atmospheres. right, would be 12 atmospheres. So all you have to do is add up the individual gases pressures and you get the total pressure of the system. See, and here's your formula for Kelvin. I'm saying it's all here, guys. All right. Turn down my phone here real quick. All right. So what's happening in the question? Let's scroll up a little bit. It's saying here you have a 1 mole sample of a pure gas or a pure bromine monochloride is placed in an evacuated rigid, right? That tells me that it's going to be, the volume is not going to change. 2-liter container at 298 Kelvin. Okay. Now it's asking you to calculate the pressure. Well, there's only one gas law that deals with pressure, volume, okay, and moles. Pressure, volume, and moles is going to be the ideal gas law. That's this guy right here. If you have pressure, volume, and moles, okay, then you have to use the ideal gas law. Now, where is that constant? Here's your gas constant right here. See, it's going to be in your cheat sheet. You have a few choices. Depending on what units you have is going to depend on which gas constant you use, okay? So let's take a look at what we have. Let's see, we have what's given to us. Well, we have 1 mole, so we know that N is equal to 1 mole. We have a volume. Let's see, we have a volume, which is at 2 liters. Okay, so we have a volume that's equal to 2.0 liters. Okay, and then we have a temperature at 298 K. Okay, so we have moles, liters, Kelvin. Okay, moles, liters, Kelvin. All right, so let's see here. For this one, okay, for this particular problem, we don't have anything in torr, so we can't use this one. And we don't have anything in energy, right? So we don't have any joules present. So the one that we're gonna use for this question is gonna be this gas constant, okay? We're gonna use that gas constant. So let's take a look at the formula. The formula says that the pressure times the volume is equal to the amount of moles times the gas constant times time. I gotta solve for pressure. So what I'm gonna do is I'm gonna bring over the V to the other side. When I do that, okay, the formula becomes pressure is equal to nRT divided by volume. Yes, that's my new formula because I'm solving for pressure. So now all I got to do is plug everything in, right? So pressure then is equal to the number of moles, 1.00 moles, times my gas constant, which in this case is 0.08206 liters, atmospheres, per moles Kelvin. Okay, that's going to be all this. I'm going to multiply that by my temperature. Scoot this over a little bit. Which is 298 Kelvin. Okay, and then I'm going to divide all of it by my volume, which is 2.00 liters. Okay, so let's simplify. Let's multiply everything across the top. So I have 1.00 times 0.08206 times 298. That gives me a total of 24.45. 388. Okay, now look what happens. Kelvins is going to cancel here. Moles is going to cancel here. Okay, so the only units left are going to be liters times atmospheres. Okay, and then divided by 2.0 liters. Now I'm going to divide that. Once I divide it, what happens is my liters are going to cancel, and my answer, whatever it is going to be in atmospheres. So it's going to be 12.22694. And my only unit left is atmospheres. Okay, the smallest number of significant figures is 3, so then I'm going to round this to 3. So 12.2 atmospheres. Remember to always have to use your correct significant figures. Okay, so that's it, guys. That's it. Those are all the gas laws. Depending on what's given to you, if you're using volume and temperature, you're going to use Charles' law. If you're given pressure and volume only, it's going to be Boyle's law. If you're given all three, it's going to be the combined gas law. And if they include moles, which is the N, then you're going to use the ideal gas law. Okay. Remember that your gas constant is going to be used depending on what you're looking for or what's given to you. If you're working with energy and you're working with joules, you're going to use the first gas constant. If it's just strictly pressure and volume with moles and temperature, then you're going to use the second one. And if for whatever reason you're working with torr, which is another unit of pressure that we've discussed, okay, then you're going to use the third one, okay? But it's just a matter of understanding which gas constant to use in that law. Also, remember that STP is 0 degrees Celsius or 273.15 degrees Kelvin and 1 atmosphere of pressure. Okay, I'll leave it there so you guys can focus on just this one, and then I'll upload another video a little bit later on today.